Now that we understand the basic concept of continuity, we're going to learn about a special theorem that has to do with it, the intermediate value theorem, which a lot of times we call IVT for short. So this theorem states, if f is continuous on a closed interval a comma b, and n is any number between f of a and f of b, where f of a and f of b aren't the same number, then there exists a value c in the non-inclusive interval a comma b such that f of c equals n. Okay, so there's really three parts to this theorem, and we're going to break it into those three pieces. So the first one is if f is continuous on a closed interval. So I'm going to draw a little sketch. I suggest you do one in your notes as well to really try and process each piece of this theorem. So we have some continuous function here without any jumps or holes or asymptotes. And we're going to look at a closed interval from a to b. Alright, the next part of the theorem says that there's some number n that falls between f of a and f of b. So first let's go ahead and label where f of a and f of b are. So if a is here, then f of a would just be its output from the function. And same with f of b. And we're saying that n is some sort of value between them. Okay, and, oh, that's not good. One important part of this is where it says that f of a can't equal f of b. Now, that seems like something obvious to say. But the reason this is part of the theorem is because, let's say instead we had a horizontal function. Okay, so I just had a flat line. If I picked an a and a b with a flat line, then in that case, my outputs, no matter what values I picked, would give me the same thing, right? So in that case, f of a and f of b would be the same, so there would be no way for us to pick some sort of n value between them where it's not all the same thing. And this will make more sense in a second, but we need to know that there's some amount of change or variance between the heights between A and B. Okay, so we'll come back to that. Okay, so we have our n, that value between f of a and f of b, and the rest of the theorem is where we get to kind of make a conclusion because of that. So if that n exists between f of a and f of b, then there exists a value c such that when I plug it into the function, I get that y value. And in this case, they're not including a and b here, so basically they're saying if n is between f of a and f of b, then we're working backwards here. That means there has to be some value c that falls between a and b. But c couldn't actually be a or b, or be equal to it, because then we would run into some issues with that part where it said these guys weren't equal. Okay? And that's, again, going back to this, the only time that really could happen is when you have a horizontal line. Okay, so this is an illustration for you of the intermediate value theorem. And again, the only reason we are able to use it is because we know the function is continuous, right? So if we didn't know if it was continuous, let's say we weren't sure about this right here. This part in between, what's even happening, right? If we didn't know the function was continuous, we could have some sort of jump here. And then that would leave us sad because just because there was a y value between f of a and f of b, it would not guarantee that there was some sort of value c that would produce it. It might not be defined at that y value at all. And just because it was between our beginning y value and end y value of the interval, it wouldn't guarantee anything. So we pretty much have to know right off the bat that the function is continuous without any jumps or asymptotes or holes, so that we're guaranteed that for any y value that exists between them, there has to be some sort of x value that will produce it. Okay, so we're going to do two quick examples using the theorem. Show that f of x equals x cubed plus 2x minus 1 has a 0 on the interval 0, 1. So remember, if a function has a 0, it means that there's some x value that produces a 0 as an output. And this is one of the ways that the intermediate value theorem is most used, because we can show that, like, if it goes from a negative to a positive output, or vice versa, it must have crossed through 0 or contain a 0 on that interval, and that's helpful for us in some of the application problems. Okay, so this is kind of a three-step problem anytime you're using the definition. If we remember, the first part of the definition was somehow showing that the function was continuous on a closed interval. Well, they give us a closed interval, so that part is usually taken care of. But we somehow need to be able to explain how we know the function is continuous. And that's where you might want to look back at the continuity videos, because there's a couple of functions that we know are always continuous on their domain. And this is a polynomial, and that's one of them. So the first thing I would simply state is that f of x is a polynomial. And so because of that, we know it's continuous on any interval. Oh, I don't know why I just wrote 1, 2. But specifically on the interval this one asks about, which is 0, 1. Okay, so the second step is to find that f of a and f of b, or the two y values that are produced from the start and end of the interval. So here I simply evaluate what f of 0 and f of 1 would equal for this function, and actually show the part where you plug it in, if this is some sort of open-ended question, free response question. Okay, so if we plug in a 0, we're going to get a negative 1, and if we plug in a 1, we're going to get a 1 plus 2 minus 1, which is a positive 2. So now I'm going to say, since we got a negative 1 and a positive 2, and we were asked if a 0 existed, well, 0 falls between negative 1 and positive 2. So that means that f of 0 and f of 1, which were the beginning and end of our interval outputs, will have some sort of value n that falls between them. So now we can make our conclusion. So according to the intermediate value theorem, there must exist a value c. Oh, hold on, not such that quite yet. On the interval 0, 1 non-inclusive, such that f of c equals 0. And that would be the end of your answer. Now the cool part here is we don't actually have to find out what that c value is. We just know that it exists, and that's all that the theorem is allowing us to say. Okay, so let's do one more quick example. Okay, so we're going to show that the function f of x equals x cubed has a value of 5 on the interval 1, 2. So again, we're not showing where it has a value of 5, we're just showing that the value of 5 exists on this graph. So again, the most important step here is also the one students most often neglect to write down, which is that the function is continuous. Because remember, if that isn't true, we cannot use this theorem. It does not work. And this particular one is continuous for the same reason as the previous one, simply because it's a polynomial. And if you come across a function that's not a polynomial, which is bound to happen, let's say it's a rational function. Let's use this one as an example. You can tell that it does have a point of discontinuity at -3, but it is also continuous everywhere else. So it's continuous on its domain. Its domain just wouldn't include -3 because there would be a hole there. Well, if the closed interval they're asking about isn't including that one area of discontinuity, then you can still assume that it's continuous everywhere else. So you would just have to state that yes, it's discontinuous at a certain value, but that value isn't part of the closed interval you're being asked about. Thus, it's continuous on that interval. Okay, so moving on to number 2, our part 2 of our explanation here. This is where we actually evaluate what f of a and f of b are. In this case, a is 1 and b is 2, and we're just plugging it into the cubic function. So that's going to give us a 1, and 2 is going to give us an 8. And so because we have a value of 5, and this falls between a 1 and an 8, we are guaranteed that there's an x value that will give us that value of 5. Okay, so because f of 1 is less than 5 is less than f of 2, we can now make our conclusion that by the intermediate value theorem, there exists a value c on the open interval 1, 2 such that f of c has an output of 5. And we're done. So again, this theorem really isn't so tricky, but it does have a lot of parts you have to make sure you write down as part of your answer. Okay, it has to be a continuous function on a closed interval. You have to prove that whatever y value they're asking about falls between f of a and f of b, and then you are able to conclude that there exists some sort of x value c that if you plugged into the function gives you that y value as an output.